Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. Now that 234 trees have given us a strategy to keep the tree balanced, we bring it back to the realm of binary trees, which are in practice much easier to work with. So RedBlack Trees, today's topic, are binary search trees that are really 234 trees in disguise. They come with elaborate rules on top of the usual BST rules to ensure that the lengths of all the paths from the root to a leaf are within a factor of 2 of each other. Not the same as in 234 trees, but within a factor of 2. That's good enough to say that they are balanced. If my explanation helps you make sense of RedBlack Trees, please click the like button. This is all very good for keeping the tree balanced, but it is not a binary tree, which in itself is a pain, because then when I visit things, I cannot just do my usual, left and right thing. I have to check for the various keys in here, check if you are outside the keys or in between keys, and then there's not the same number of keys and so on. It's not so fun to write code for the 234 tree because of the variations in the nodes. So we would like to have this property of being balanced, but with a binary tree. And so we build a binary tree that's modeled on the 234 tree by using a trick that converts 234 nodes into binary nodes. And how you do that? You do that by saying, I will consider a 2 node. That's already a binary node, that's fine. I can use it as it is. A 3 node, one with 3 children, that's a bit more annoying. And a 4 node, well, I'll take inspiration for the 4 node from what I did over here. And so I will convert this 4 node into a cluster of 3 binary nodes, which altogether have a parent, and 4 children, same as the 4 children of this guy. And yes, well, the only thing that is slightly annoying is that now I have 2 layers of nodes in my replacement cluster, but we'll deal with that in a moment. So in here, I have no conversion to make. And in here, I can do something where I only add the extra child on one side, or it could be on the other side. Doesn't make a difference externally. But I end up with 3 children, 1 parent, one way or the other. And externally, these clusters look the same as the 2, 3, 4 nodes that they replace. This one from outside looks the same as this one. Now, this tree was nice and balanced. The tree that I make by replacing these 2, 3, 4 nodes with these clusters according to these rules, is it going to be balanced? Well, it's not going to be that far off, because at worst I increase things by 2 on some paths and I don't in some other paths. So the worst it could go out of balance is that some paths are twice as long as some other paths. But it could not be that some paths are 10 times as long as any other paths. That could not happen. However, things could get worse if I then start manipulating a tree, inserting things in, deleting stuff, then everything, all kinds of bad things could happen, and I don't want that. So I really want to keep the shape and essentially the treatment of the 2, 3, 4 tree while being binary. So what I do is the following trick. This is where the red-black business comes from. I will consider the binary nodes that I've made as of 2 different types. there's going to be the black ones that correspond to the 2, 3, 4 nodes that I had, and the red ones which are going to be auxiliary things to make up for the fact that the binary nodes don't have enough children. So for every one of these, so this one corresponds to this one. This one corresponds to this one. That's like the boss of this cluster of 2 nodes. And this one corresponds to this one. That's the boss of these 3. The others, the minions, they're red. So that's a minion, and that's a boss. So if I view things this way, then I can see that every 2, 3, 4 node corresponds to a cluster that always has a boss, one boss, and potentially some minions, not necessarily. So if I do that, on every path from the root to a leaf, I will have one edge coming from the 2, 3, 4 tree, and maybe one edge coming from the inside of one of these clusters, or maybe not. And the edges that are added will go between a black and a red node, and the edges that are from the 2, 3, 4, 3 will go from something that could be red or black, depending on how the cluster finishes, to a black node. So all these edges here will end in a black node because they will touch on a boss. So if I transform this using these rules, I obtain what is known as a RedBlack tree, which works according to these rules. Forget about it. Will I ever be able to get back to this? Nobody knows. This, okay. This is from your handout. Every node is either red or black. The root is black. All leaves are black and never contain key value pairs. So you should imagine that at the bottom you have some extra layer of leaves like this that are just there for decoration and to mark the end of the tree. They don't contain any keys or satellite data. Number 4, if a node is red, then both its children are black. Obvious, because its children start with the boss, which is black. They correspond to new nodes in the 2, 3, 4 tree. For each node, all paths from that node to descendant leaves contain the same number of black nodes. I've always said this from the root, but it actually works from any node. From any node, the paths to leaves will have the same number of edges and in the 2, 3, 4 tree. And in the RedBlack tree, what matters is that there's going to be the same number of cluster derived from the 2, 3, 4 tree, each one of which corresponds univocally to one black node, which is the boss of that cluster, and therefore you have a bijection between the black nodes and the nodes in the 2, 3, 4 tree. And therefore, all paths from any node to descendant leaves contain the same number of black nodes. And in any path, you can only have either black nodes following black nodes or alternation of having red nodes in between, but you can never have consecutive red nodes. And so this guarantees that in any path, I will have at the minimum the number of edges that are necessary to connect these black nodes, and at maximum, it's going to be bounded by twice as many in the case that I have red nodes interspersed. So this is what keeps my tree not exactly balanced, but fairly balanced, is that every path length is within a factor of 2 of each other. And this is enough to guarantee that overall the size, the height of the tree will be logarithmic in the number of items in it. It doesn't have to be exactly the same length, but so long as they are within a factor of 2, then I can easily prove that the height of the tree is going to be logarithmic. But I am spending perhaps too much time on the easy stuff. What matters more for us is to see what we should be doing when we alter a tree like this. So to do that, we need to introduce a special operation which we haven't seen so far, which is called a rotation. So this is a tree I prepared at home, and the rotation is applied to an edge of the tree, for example, this edge. Rotating this edge means A was the parent of C. I'm going to make C the parent of A. So this means rotating the edge like this. C now is the parent of A, but C had children, so the children should go together with C. And I see that this doesn't work because this F was the left child of C, but now if C becomes the parent of A, it's A that should be the left child of C. So this rotation looks like a nice idea, but doesn't work. Because what do I do with the left child? And the answer is, well, it does work if what I do with the left child is I stick it here. Because A used to be C as its right child, but now no longer has C as the right child because C has been promoted to being the parent. So the right child of A has disappeared. It's become A's parent. And so there's a space where I can attach what used to be the left child of C. Why is this a neat invention? Because maybe this choice of letters was not the smartest I could have done, because this is not in a configuration where they match the BST properties. So this should be something where, as far as the keys, so don't read these as the keys, read them as the designators of the nodes. But if I were to put keys and this were a search tree, then it should be the case that everything in the left subtree is smaller than the root, which is smaller than everything in the right subtree. So I would have something along the lines of 1, 2, 5, 7, 10, 15, 20, something like that. And again, I have committed the usual sin of doing things that are not going to move around when I move them. So, yes, well, if I were now to move C to where it was, C has a child which is 10, because it's a left child, is smaller than 15. But because it's in the subtree of C, which is the right child of 7, then it is bigger than 7. So things in this zigzag have the property that they are bigger than 7, but smaller than 15. So 10 is between the 7 and the 15. The neat thing about this arrangement is that, and excuse what will happen to the green numbers, if I now move this C, if I now move this C to here, this used to be the 15, used to be the 15 parent of 10, is still going to be the parent of the 20, but this 10, which was orphaned from the 15, if it's reparented as the child of 7, it still is a 10 that's bigger than 7, and that is smaller than 15 because it's now in the left subtree of 15. So it is still between the 7 and the 15 in this new configuration. So it used to be like that, and it works like that instead. So this works just as well as this worked. So the rotation of this edge to go here has preserved the search tree properties. And so whenever it is more convenient for me to rearrange the tree, moving things up a level, I can do that with this rotation while preserving the properties. Of course, nothing has changed for this because it was the right child of 15 still remains. Nothing has changed for this because it was all the subtree that was on the left of 7, and it still is. And the only things that changed, we verified that it works for them. And so this means with a local change, which only involves a fixed number of pointer manipulations, regardless of how big the subtrees are over here. So all these subtrees could contain millions of nodes. I still change the same number of pointers when I do a rotation. With a constant cost, I can do a rearrangement that preserves the search tree property for all the nodes in here. So with that said, we have enough weapons in our arsenal to tackle the actual insertion into a red-black tree. There are fairly complicated rules in your textbook for how to handle the insertion in order to preserve these invariants of the red-black tree. And because I am working on the basis of doing the things that worked for the 2, 3, 4 tree, I will still have to insert my new node only at the bottom. I cannot insert in the middle, otherwise I mess up all this neat structure of levels. If I insert something at the bottom, what are the nodes going to look like? Well, the nodes at the bottom are going to be black if the bottom node is a 2 node, are going to be red if the bottom node is a cluster, like a 3 node or a 4 node. In either case, what I insert into that, should it be red or should it be black? If I have my final level over here, and I try to insert a black node, black nodes are the ones that are the heads of levels. And so I'm basically making another level. So that's clearly not nice. I should try to insert a red node, because a red node doesn't generate a new level. Now, inserting a red node is good if I'm inserting it into a cluster that represents a 2 node or a 3 node. If I'm inserting into what was already a 4 node, so already finished with 2 of these, then I cannot legitimately append another red node in here, and I am into some kind of trouble. But you realize that if it's like this, then adding a red node is not a problem. It means there is space. If it's black at the bottom, there's space to add a red node. So the only thing I really need to be concerned with is adding a red node in the bottom layer to a parent that is red. And I have to fix things up so that the result is a red-black tree. So node to be inserted, which we are going to be calling n, is red. And the parent of the node to be inserted, which we're going to call p, parent, is red. Because if it were black, I wouldn't have to do anything other than just inserting it, and that's done. So if it's black, it's even better. But if it's red, I have to talk about how to do it. There are 3 cases depending on the uncle of n. I say, well, what's that? Well, if you have a parent, then this parent, because it's a binary tree, has up to 2 children. So the parent of the parent, so the grandparent of the node I'm inserting, will have up to 2 children. And these 2 children, one of them is the father, and the parent, and the other one is the uncle, as in the brother of the parent. So this uncle, what color is the uncle? The uncle could be red, and this is our case number 1, or the uncle could be black, and this is our case 2 or 3. And the difference between 2 and 3 is whether, in the case of 2, then I have a zigzag between grandparent, parent, and my node. And in the case of 3, it's straight. These are the 3 configurations I need to check. Of course, in here, I could also have a zigzag in the case of inserting red into red with the red uncle. But whether I have a zigzag or not doesn't change what I do, so I can consider all of that as part of case 1. What do I do in case 1 is the following. I look at this and I say, well, inserting this into here will violate the rule that if a node is red, both its children are black, because that would make it 2 consecutive reds. And so I'm going to change things by making these 2 guys black. Okay. So becomes black, becomes black. Now I got myself a problem 1 level up, because I'm violating, well, no, I'm not violating this anymore, but I have introduced more blacks. I've basically introduced an extra level, so I've unbalanced what used to be the 2, 3, 4 tree. So to remove that imbalance, I'm going to make the parent red. And if I've done that, then locally this tree is fine, but it's almost as bad as my initial thing where I've inserted a red node. And so I have to basically redo the same operation 1 level up until I no longer create a problem for what's up. Because if the parent of this one, if the parent of the grandparent, so if the great-grandparent were black, then everybody's happy. But if the great-grandparent were red, then I have a red, and I have to redo this operation. So this may involve keeping going up until I insert into something where the parent above this thing was black. So that's case 1. Now case 2, in case 2, what I'm going to do for case 2 is to transform it into case 3 and then solve case 3. And I transform it into case 2 by doing a rotation of this PN edge. So rotating this PN edge, transforms me into something that shape-wise looks the same as case 3, even though the nodes that are in here are not the same, because my new node is here instead my new node is here. But that's irrelevant to the shape and the colors of the tree. I'm first recoloring these 2. I'm swapping the colors of these 2. So this one becomes black. And this one becomes red. And after that, I do a rotation of this other edge. It will never work. Okay. So red, this one became red, and this one became black. So now this has the right alternation of colors, and I no longer have my 2 consecutive reds, and I still have the two layers between the 2 bosses that I had before. Used to be 2 blacks, the grandparent and the uncle, and now it's the parent and the uncle, and the grandparent has been slotted in this way, so that if I compare it with the original configuration that I have now lost, but which you have at the top of page 108, you can see that between grandparent and uncle there were 2 consecutive blacks, which is a kind of a waste in this sense. So I managed to insert some red between those 2 blacks, making use of the capacity of that black, and that's how this configuration works. So this has transformed all the cases of inserting something into a RedBlack tree to something I can actually do with a binary tree while preserving the global invariants of the 2, 3, 4 tree, which are translated into those seemingly arbitrary rules about red and black. So because all these things I've done preserve these things, they also preserve the 2, 3, 4 tree properties, and it means all the paths are still within a factor of 2 of each other, and so the tree is overall balanced. And it's a bit of a pain to program something like 2, 3, 4, like RedBlack Trees, because there are so many different cases, but it's still easier on the programmer than programming the 2, 3, 4 trees. So that is why 2, 3, 4 trees have been supplanted by this binary variant. But if you only study the procedures that are given to you for RedBlack Trees, as in your textbook, without having had a glimpse of 2, 3, 4 trees before, it is slightly difficult to understand where all this came from, and this is why I took this little detour. All right, so if you do take your textbook, there's a worked example which I urge you to work through. It looks a bit like this, and there's a tree with red and black nodes, and you are inserting a red node into a red node over here. And so what happens, this is first the case 1, because the parent is red and the uncle is also red, and so you do the recoloring of this, and it's over here, and then this brings you to the same thing, that you're inserting a red into a red over here, and this is a case where this is your parent, your uncle is black, so that's case 2, and so you have to do the flipping it so that it becomes case 3. So you rotate this edge to 7 to bring it over here. You notice that this remains here. This is the child that changes parent, so it becomes here, and this one stays where it was. The rest of the tree is unaffected. Having now transformed this into case 3, I have a straight line between my new node and the parent, and then the uncle is black, and then I recolor the this is the thing that I did in the wrong order. So I recolor this and this, recolor to this, and I rotate this edge. So this one goes down, and this one changes parent to become child of 11. And then I'm left with something that is now, whoop, so the red's gone. Take this and group them together. I hope this will let us do this. Yes, and then you're left at the end with something that is a valid red-black tree. You can see there's one neat level of the root, which is a 4 node, and then a neat level of this, which is the bottom cluster of non-empty, of non-leaf nodes, which some of them are 2s and some of them are 3s. There's no 4, but every path to the leaves is with just 2 black nodes, and sometimes a little more because of the reds, but never more than a factor of 2 from that.